Dear 11th class students, today we are going to learn about square root of a complex number. So here there is a theorem for this. Of course, proof is not required. Just I am writing the statement. Please note down perfectly without a single mistake so that you will get right answers. Root over a plus ib is equal to plus or minus root over mod z plus real part of z by 2 plus I into root over mod z minus real part of z by 2. See the formulae, both okay or same in either cases, but only different is here there will be plus, here there will be minus. If that b is greater than 0, that means this imaginary part of z, that b, if b is greater than 0, here you have to take plus. If b is less than 0, here you have to take minus. But in either cases these terms are same, you see, the terms are same. So you have to understand one main point here. To find square root of a complex number z, the major role mod z and real part of z. The rest of the things the same. Root by 2, this plus here, there minus here. If b greater than 0, here plus. If b is less than 0, here minus. The terms here and here are same. Understood? Now we will do one problem. Find the square roots of the following complex numbers. First, our heading is find the square roots of the following complex numbers. That is our heading. First question, z is equal 5 plus 12i. When this is compared with standard form, okay, a is equal to 5 and b is equal to 12, which is greater than 0. Now we need to find mod z. Mod z is equal to, yesterday I explained mod z is equal to root over a square plus b square, root over 5 square plus 12 square. 144 plus 25, 169, root 169 is 13. And real part of z, which is a, which is 5. And b is greater than 0. You please do remember. Now root z, which is equal to root over 5 plus 12i, as I have given, plus or minus. Do you understand what is the formula I have given? Plus or minus root over mod z, which is 13, plus real part of z, which is 5, by 2. As b is greater than 0, here you get plus I into root over mod z minus real part of z by 2. So this is equal to plus or minus 13 plus 5, 18, 18 by 2 is 9, plus I into root over 13 minus 5, 8, 8 by 2, 4, which is equal to plus or minus 3 plus 2i. This is the square root. Understood? Our next question is find the square root of 7 minus 24i. So when this is compared with standard form a plus ib, so here a is 7 and b is minus 24, which is less than 0. So now you have to calculate mod z and real part of z. Mod z is root of 7 square plus minus 24 whole square, which is equal to root 625, which is equal to 25. Real part of z is equal to a, which is 7. Therefore, square root of z is equal to plus or minus, I said no, plus or minus root over mod z plus real part of z by 2. Now as b is negative, you get minus I into root over mod z minus real part of z by 2. It's called plus or minus root 16 minus I into root 25 minus, this is 25 plus 7, 32, 32 by 2 is 16. Now 25 minus 7, 25 minus 7 is how much? 18. 18 by 2, 9. This is called plus or minus 4 minus 3i. This is the answer. Understood? Now dear students, representation of a complex number. A complex number can be represented in geometrical form and in polar form. Polar form means trigonometric form. Understood? So, representation of complex number. A complex number can be represented in geometrical form and polar form. Polar form means trigonometric form. So, now geometrical representation. Geometrical representation of a complex number. So, geometrically complex number is represented by an ordered pair of real numbers. It is very simple. Geometrically a complex number represented by an ordered pair of real numbers. Right? Here x is called real part, y is called imaginary part. The real part we choose along x-axis and imaginary part we choose along y-axis. So, as we take real parts on x-axis, it is known as real axis. And these imaginary parts as we take on y-axis, it is known as imaginary axis. And a plane of xy axis that contains complex numbers is known as Argonne plane. Did you understand? The plane which contains both xy axis, which represents respectively real axis and imaginary axis, is known as Argonne plane. A complex number in this plane is represented by a point pxy, which is as it is xy means x plus iy here. Understood? So, this is the geometrical representation. Understood? Geometrically, a complex number represented by a point in the Argonne plane, a point pxy in the Argonne plane. Here x is real part, we take along x-axis, y is imaginary part, we take along y-axis. So, hereafter we shall not make any distinction between the ordered pair and the standard form of a complex number. So, the point P takes the responsibility to represent x plus iy. Understood? Now, What is the geometrical meaning of modulus of the complex number? See, as we have discussed, mod z is root over x square plus y square. This root over x square plus y square is nothing but here distance from origin to the point P, whose coordinates are x comma y. So, modulus of a complex number geometrically represents the length of the line segment OP. Understood? If you use distance formula to find the length of the line segment OP, where O stands for origin, P stands for xy, and use the distance formula, you get this only. Understood? So this is about geometrical meaning of a complex number, geometrical meaning of its modulus. Now we are going to discuss another term, argument of complex number z. This is important here. Argument of complex number z. Argument of z is defined as the angle made by OP with the positive x-axis in the positive direction. Suppose this is theta. Theta is known as argument of the complex number z. So it is denoted by arg z. Argument means the angle made by the ray OP with positive x-axis in the positive direction is known as argument of z, and it is denoted by arg z. Understood? Now finding argument of z. See, from trigonometry we have tan theta is equal to y by x. You have learned in trigonometry tan theta is equal y by x. Then theta is equal tan inverse y by x. But calculation of argument of z, okay, using this formula has a drawback. Here there is a drawback. Let us check it out. What is the drawback we have in calculation of argument of z using this formula? Okay, I am explaining you drawback. Okay, suppose take a complex number z. Okay, say for example this is 1 plus I root 3. Say 1 plus I root 3, right, which represents the point 1 comma root 3, which is in quadrant 1. So this is the complex number z1. Now what is the argument of this? So tan inverse y by x means tan inverse root 3 by 1, which is equal to tan inverse root 3. Right, now let us take another complex number z2. Say it is minus 1 minus I root 3. Okay, which represents the point minus 1 comma minus root 3, which is a point in third quadrant. Now let us find out argument for z2. So tan inverse minus root 3 by minus 1, which again gives you tan inverse root 3. So two different complex numbers z1 and z2 which lie in different quadrants. Are you following? These two complex numbers are different. They lie also in different quadrants, but having same argument. So that is the drawback you have in using this formula. So don't never use this formula at all to find argument of a complex number z that gives throws you in a wrong direction. So here, so that is the reason we are saying this is a great drawback. So z1 and z2 are two different complex numbers which lie in different quadrants, have same argument. That should not happen, right? Different complex numbers in different quadrants, how can have same argument? So please don't use this formula to find argument of z at any cost. Okay? Argument of a complex number depends on the quadrant in which the complex number lies. So argument of a complex number strictly depends on the quadrant in which the complex number lies. In fact, it is the simultaneous solution of argument of z is the simultaneous solution of the two equations cos theta is equal x by root over x square plus y square and sin theta is equal y by root over x square plus y square. So now you can use this successfully to find argument of z. Argument of z is equal to theta, where theta is the simultaneous solution of these two equations, this and this. Using this, you will not be having any problem. So you can use these two equations to get argument of z. Understood? So here you have to note a point clearly, that argument of z depends on the quadrant in which the complex number lies. Again, the simultaneous solution of these two equations leads to infinitely many solutions. The simultaneous solutions of the above two equations are infinitely many solutions you can get which can satisfy these two equations simultaneously. So why do we need infinite arguments for the same complex number? See, what is that so necessary to have infinite arguments for a same complex number? Is it one is not sufficient? So mathematicians what they did is they took strict limits. Within the limits only they want to search the argument, so that they can successfully find only one argument within the limits. So that is called principal argument. So now we are talking about principal argument. Principal argument means there exists only one argument, there exists only one theta. There exists only one value for theta in minus pi is less than theta is less than or equal to pi. Within these limits, Don't think more than required about the limits. Mathematicians themselves set these limits. So there exists only one value for theta in minus pi is less than, theta is less than or equal to pi, satisfying these two equations. Satisfying 1 and 2 simultaneously. Understood? So there exists only one solution, okay, within these limits. It can satisfy both 1 and 2 simultaneously, and that solution theta is known as principal argument. This theta is known as principal argument. And unless otherwise stated, argument means principal argument only. So the examiner is asking you to find argument, means it is a principal argument. Unless otherwise some limits have been mentioned. Suppose the examiner is choosing, okay, some limits, and okay, in that interval suppose is asking you to write all possible arguments, okay, then okay, that is a secondary case. But suppose just you were asked to find simply the argument, you have to search within these limits only. That means you have to find only principal argument only. Understood? So dear students, now we are going to have an important discussion, that is argument of a complex number in various quadrants in Argonne plane. Here throughout our discussion, this z is a complex number x plus iy, which is equal x comma y, which represents the point P in Argonne plane. Throughout this discussion, okay, these all are, okay, taken as granted. Z is a complex number which is x plus iy, which is ordered pair xy, which represents the point P in the Argonne plane. And alpha is an acute angle. Alpha is an acute angle satisfying tan alpha is equal y by x modulus. Okay? So alpha is the second point that you have to take it as granted is alpha is an acute angle satisfying tan alpha is equal mod y by x. Okay? And theta is the argument of complex number z. Right. Now let us invite 4 cases, because there are 4 quadrants. Okay, if the P belongs to Q1, that point P is in quadrant 1. So we are choosing P so that it lies in quadrant 1. Okay? This is theta. So if P belongs to Q1, right, then obviously x is greater than 0 and y is greater than 0. Okay? Then tan theta is equal y by x. Obvious, tan theta is equal y by x. And tan alpha is equal mod y by x. Here I define tan alpha is equal mod y by x, and where x greater than 0, y greater than 0. So mod y by x is nothing but it is y by x. Are you following, dear students? Then tan theta is equal tan alpha, and hence theta is equal to alpha. So when P belongs to Q1, theta is equal to alpha. So our argument of Z is nothing but theta alpha. You can take any symbol. So in this case, our argument of Z is equal to alpha or theta is equal to tan inverse y by x, provided if the point P lies in Q1. So this is the most important point that you have to understand. Understood? Right. Dear students, now we are discussing case 2. Case 2 is when P belongs to Q2. The point P is in quadrant 2. Then what will happen? It is obvious that x is less than 0 and y is greater than 0. Right? Right? And tan alpha is mod y by x. Now it is very clear that here theta is equal to pi minus alpha. Is it clear? Theta is equal to pi minus alpha. In this case, our theta is equal to pi minus alpha. Because these two angles together form a linear pair. So obviously, theta would be equal to pi minus alpha. Okay? So if P lies in quadrant 2, x would be less than 0 and y would be greater than 0, and our tan alpha is equal to y by x, and the argument of z, which is equal to theta, here is taken as pi minus alpha, where tan alpha is equal mod of y by x. That is standard. Understood? Now, if the point P belongs to Q3, okay, theta is the argument of Z. So, argument of Z is theta, okay, which is clear that it is equal to pi plus alpha. So, argument of Z is theta. See, in the diagram you are seeing, it is equal to clearly pi plus alpha. But pi plus alpha is not a principal argument. It is argument only, but it is not principal argument because it is crossing pi. So, if you want a principal argument in this case, okay, you can take as pi minus alpha minus of pi minus alpha you can take. Because this whole thing is pi and this is alpha, okay, so this would be pi minus alpha, but it is in the negative direction, so it will be minus of pi minus alpha. Understood? So here we are taking argument of z as minus of pi minus alpha. Why? Because this whole thing is pi and this is alpha. Okay, so if you consider this is an argument now, okay, so it is minus of pi minus alpha, because that you are taking now in the negative direction, so negative sign will come, minus of pi minus alpha. Okay, So if P belongs to Q3, argument of Z is pi plus alpha. Okay, this is 100% perfect. But if you are not interested in just argument, if you are only interested in principal argument, so if you go for principal argument, argument of Z can be taken in this case as minus of pi minus alpha. Okay, so please take care of that. If the questioner is not insisting on principal argument, you can find this or that, or you can find both and you can write the argument is this or that. Okay, your wish. And last case, if the point P is in fourth quadrant, okay, it is clear that argument of Z is equal to theta is equal to, okay, 2 pi minus alpha. Right? It is very clear. 2 pi, this whole revolution is 2 pi, that part is alpha. So this part is 2 pi minus alpha. So, but again that same situation will arise. 2 pi minus alpha is not principal. This is not principal argument. This is not principal argument. So to get principal argument, okay, you have to see the angle in the negative direction. So angle in the negative direction would be minus alpha. So therefore, okay, for principal argument, you have to take theta is equal minus alpha. Okay, so if point P lies in fourth quadrant, our argument is 2 pi minus alpha or minus alpha. Okay, if you want the argument within that specified limits, suppose okay, in a natural way it is crossing that specified limit, you have to go in the anti-clockwise direction. Okay, that ray remains same, but clockwise, okay, it is theta, and anti-clockwise it is minus alpha. So theta is equal minus alpha. Understood? So dear students, now we are solving small examples. Find the arguments of the following complex numbers. So first let us take Z is equal 1 plus I root 3, which represents the point 1 comma root 3 in Argonne plane. Therefore here P is equal 1 comma root 3, P belongs to Q1. Did you understand? Then argument of Z equal to theta is equal to alpha. Okay, and is equal to tan inverse y by x. We have learned now, just now. So therefore argument of Z is equal, theta is equal tan inverse y is root 3 by x is 1. So tan inverse root 3. Okay, so tan inverse root 3 is 60 degrees or pi by 3 radians. So argument of Z is pi by 3 radians. Ante, that's it. Understood? Now let us take second one. Now I have solved first one. Now let us take second one. As Z is equal minus 2 plus 2I root 3, which is equal, now this Z is represented by the point minus 2 comma 2 root 3. So here this minus plus, so this P lies in second quadrant, right? Understood? Now calculate alpha. Alpha is equal tan inverse, alpha is equal tan alpha is equal tan alpha is equal mod y by x. So implies tan alpha is equal mod y is 2 root 3 by minus 2 equal to mod root 3. So tan alpha is equal root 3. So alpha is equal, okay, pi by 3. Alpha is equal pi by 3. As P belongs to Q2, therefore argument of Z is equal, theta is equal pi minus alpha. Already we have discussed. So this implies argument of Z is equal, theta is equal pi minus pi by 3. Okay, which is 2 pi by 3. So this is the argument of Z for second complex number. Now third one. So Z is equal minus root 3 minus I. This represents the point P, okay, minus root 3 minus 1. Therefore P belongs to Q3. Right? Now calculate tan alpha equal to mod y by x is equal to mod minus 1 by minus root 3, which is equal to 1 by root 3. Okay, is equal to tan pi by 6. So tan alpha is equal tan pi by 6. Therefore alpha is equal pi by 6. So if you go for principal argument, therefore argument of Z, as I discussed, okay, when the point in Q3, argument of Z is minus of pi minus alpha. That's what we have discussed now. This is equal to minus of pi minus pi by 6. Minus of 6 pi minus pi, pi by 6. This is equal to minus pi by 6. And last, fourth one. Z is equal 2 root 3 minus 2i. So this represents the point 2 root 3 minus 2. Therefore it is plus minus. So it is in Q4. So calculate tan alpha. Mod y by x. Mod minus 2 by 2 root 3. Which is equal to 1 by root 3. Therefore alpha is equal pi by 6. So when Q is, when the point P is in Q4, so what is the argument of Z as we have discussed? Minus alpha. So argument of Z is equal minus pi by 6. So this is how we have to calculate argument of a complex number.